Hi, hello everyone. I'm Cody. I'm a software engineer at Anyscale, and this is Philipp, the CEO of Anyscale. Today, we're going to cover LLM Inference at Anyscale. So this will be the outline for today. Basically, we'll mainly cover 2 points. One is Anyscale open source contributions, and the second is Anyscale proprietary inference capabilities. So let's start from the first point. We know that vLLM is now one of the most popular LLM serving engine in this world and has been adapted by many companies as their production use cases. And it's been over 500 contributors with 27K stars in their GitHub repository. And in the past 6 to 8 months, Anyscale has spent a lot of efforts investing on the open source vLLM, especially on the performance implementations. For example, Anyscale was leading the following open source features, which are actually pretty critical in the current vLLM performance. There is an API support joined with the neural magic, which gives you the fast computation and less memory footprint. And it also contributes to scheduling with the trunk prefill, which is able to maintain the low inter-token latency for long context requests. And then we also contribute the speculative decoding framework, which reduces the inter-token latency by more than 2x for the low QPS serving cases. I will dive into all of those 3 features in the rest of this talk. And in addition to that, we also contribute many more features like multi-step scheduling to reduce the CPU overheads. And you also contribute efficient pipeline comparison with the Ray-compiled graphs that you will be hearing more details in the following talk given by Sen and Morali. And we also contribute the visual language model support joined with the Roblox to bring the multimodality model into vLLM. Finally, we also contribute multi-LoRa support so that you can serve multiple LoRa weights with the same model engine. Now let's dive into some critical features that's being used by vLLM day to day. The first one is the API support on NVIDIA GPUs. Again, this is the joint work with the neural magic. So first of all, why API is critical in LLM serving against FP16? First of all, we can see that the quality. FPA is able to achieve 99% quality against FP16. And it's extremely easy to quantize so that you can directly get the performance benefit and the memory benefit by just quantizing the model to FP8. And you can see the benchmark on the right-hand side. By benchmarking the Llama 3.170 model on H100, you can get up to 1.27 TTFT improvement time to the first token and 1.5x ITL inter-token latency improvements. So it's more like almost a free lunch and low-hanging fruit to give you the speed ups. But what's the challenge to support FPA in vLLM? The first thing is to standardize the FPA checkpoint format. By the time you want to support FPA in the vLLM, FPA is not that quite common in this world. So we collaborated with the neural magic forks to figure out the reasonable FPA checkpoint formats and support that in the vLLM. And fortunately, this format has been widely used now by many models. So vLLM is able to load those models and work just out of the box. And the second thing is we have to support the FPA quantization framework in the vLLM in terms of how to load the model, quantize on the fly, or execute the model in an efficient way. And finally, we of course need efficient FPA CUDA Trident kernels to fully utilize the FPA tensor cores available on GPUs. And fortunately, now FPA is being widely used in the vLLM, and it's become some of the default options for large models. For example, Llama 405B, FPA version becomes one of the official first release by Meta. The second feature I want to highlight is the trunk prefill. This is also a critical feature used in vLLM today. First of all, why trunk prefill is critical? Because trunk prefill can chunk the long prompt into the small chunks and run it in several batches. By this way, we can limit the number of batch tokens to maintain the low latency, which means you can improve your interlocal latency and you can batch the prefill and decode requests together so that your decoding won't be interrupted by your prefill requests anymore. So here are some experimental results. You can see that simply enabling trunk prefill in the Llama 3.170B model in the H100, you can get up to 1.4x ITL improvement by only paying 30% TTFT slowdown. And this is expected because we chunk the prompt into multiple batches, but just 30%, and it can give you better ITL. You can likely meet your SLA in a better way. And again, this is not a free launch to support trunk prefill in the vLLM. First of all, we have to integrate append kernels to the vLLM. Before that, vLLM attention kernel can only process the prefill or decode, but not mix of them. And we have to first integrate the kernel to make it available, and then we have to refactor the request scheduler and support prompt chunking. Finally, you have to schedule both prefill and decode requests in the same batch, and then they work together. This requires a lot of refactoring in the vLLM architecture, and we're glad that it's already landed and already available in the recent vLLM release, and it's now become the default on option when you're serving most of the models. And then I'll pass to Philipp to introduce the speculative decoding efforts.
So speculative decoding allows to significantly reduce the latency of requests. And let me explain a little bit how this works. So GPUs are very good at processing batches of data in parallel. And actually to the degree that for decoding, it's often the same performance to decode a single token versus decoding multiple tokens. So by default, you can't use that for decoding, at least not in a single request, because in order to get the future tokens, you have to first have the current token. So you can't really decode into the future. But speculative decoding allows you to change that. It uses a small draft model to quickly compute a bunch of tokens ahead, and then the whole batch can be verified by the big model. So it will get the same output that the big model would give, but if the big model agrees with the small model, then you get a decent speed up. So in this case, for example, we would have like 3 tokens, and 2 of them got accepted, so we got like an almost 2x speed up. So we have contributed a speculative decoding implementation to vLLM, and we have also been working on special speculation models that are performing better than open source models. So like on the Anyscale platform, you can just use those, and you can also fine-tune them on your own data. The challenges on supporting speculative decoding was changing the block manager so it could pre-allocate the slots for the speculative decoding, and then also integrating the draft model into the LLM engine. And then also there's a decent amount of systems overhead that we needed to reduce to make the speculative decoding fast. And here are some results of this. So on the left-hand side, there's a graph that shows speculative decoding in the context of prompt lookup, where, so this is the case when you have tasks like summarization or RAG, where during decoding, there's a decent amount of repetition from the prompt. And then during the decoding, we do string matching against the prompt, and if there's token overlap, then the speculative decoding will be effective. On the right-hand side, you see a more generic setting, where it's just arbitrary prompts, and there we use a small LLM to do the predictions, and then get speedups that way. So typically you can get speedups on the order of like 1.5x to 2x using this technique. I wanted to also say a few words on how we view the future of vLLM and what are the important things here. The reliability is really paramount. So we've actually spent a decent amount of time working together with the Berkeley team to improve the code structure, but also really improve the testing coverage, to add many more tests. And then also one of our engineers actually is maintaining the CI, so making sure that things will just get more and more stable over time. One thing that is really great about vLLM is the comprehensive feature set. So it covers many of the features, some of them that I just talked about, but also many different models and many use cases, multimodal support and things like that. At the same time, while being very comprehensive in the feature support, it's very important to be composable and have a minimal core that is extended by these features, so that everything stays maintainable and testable and stable. So we've been working on refactoring things so that some of the things can be plugged in, like for example, logic processing and JSON processors, or like the executor or the scheduler, things like that. And then it's also really great to be open source, and there's a big community due to its Python and PyTorch roots. It's very easy to contribute things and to adapt new models, so it can always catch up with the latest LLM trends. Okay, let me now switch gears and talk a little bit more about the proprietary inference capabilities we have been developing at Anyscale. So first of all, I'll give you an overview of our inference stack. So at the bottom is the Anyscale platform that is powered by Ray, which is the AI compute engine that is integrated with a comprehensive ecosystem for all kinds of workloads, including unstructured data processing, training, and also inference. There's many features that connect to the underlying infrastructure to make it better, more automatic and reliable scaling. And also we spend a decent amount of time investing into the development experience to make that really smooth. And then on top of that is the inference engine, and that is based on vLLM. And then we have some proprietary features that I'll be talking about in a bit. And on top of that are the applications. So we support online serving with RayLLM and RayServe, and then offline batching with RayLLM Batch. We will talk about that in a little bit. So first I wanted to talk a little bit about the accelerated inference kernels that we've been developing. So this is really a set of kernels that supports a more restricted set of features and models, but really it's really optimized for performance. So we can do things that you can't do with open source codes, like optimizing the memory layout, doing the optimal coalescing, and then doing like PTX level optimizations. And in particular, we can put all the operations of the decoding into one kernel. That's something that open source typically doesn't do. Fusing together all the operations like matrix multiplications, FP8 conversions, RMS norm, rope, CLU, and then keeping the data in registers and shared memory as much as possible. And the code base is actually the same code can also run on different hardwares, including CPUs with the AVX and AMX instruction set, and GPUs, including A10G, L4, and H100. But we build it in such a way that it's extendable with plugins. So the same code base can run on these, and then there's plugins for the different hardwares. So here's some preliminary results. We are still improving them, but at the moment we get like a 15 to 30% speed up for decoding. So on the left-hand side there is the ITL for Llama 3.8b on H100 with FP8, and then on the right-hand side there is Llama 3.8b decoding on A10Gs with FP16. The next thing I wanted to talk about is RayLLM for online serving. So this is LLM serving on top of RayServe, so it inherits all the great properties of RayServe. Things like model management, model multiplexing, so multiplexing multiple models on a single GPU, downscaling to 0, and then also we have some specialized features that are specifically great for LLMs, like fast model loading, fast JSON mode, and everything is well integrated with the Anyscale platform. And so if you sign up with Anyscale, there's a one-click template where you can deploy this. And it also it's great because it's very easy to get started, but it also has all the knobs for configuration exposed, so you can tune it for your particular workloads. Cool. The next thing is about RayLLM Batch, and Cody is going to talk about that.
Right. So Philipp just introduced RayLLM. This is the perfect solution for your online serving to deploy your private endpoint. But on the other hand, we want to emphasize that the batch inference is also an important workload, especially in the recent months. Why batch inference? Because in the batch inference, you can actually minimize LLM serving cost by maximizing GPU utilization and throughput. So if you have some downstream tasks that you don't really care about the intermediate reaction in terms of latency, then you can try to use LLM batch to save your money. For example, if you want to process a document, summarize the document, etc., then you can consider use batching. And if you want to use batching processing, why you want to consider RayLLM batch? Because we first provide the simple API with the Ray data. I'm showing the code snipe in the right-hand side. You can see that you can easily define your workload using this data class. The only thing you need to do is to specify how the data will load it using the Ray data API. For example, your data is JSON or other formats. And then you can choose how to pass that data in any format you like and then feed into the LLM. And after that, the only thing you need to do is to provide its workload along with engine configuration. And then that's it. You are creating the Ray LLM batch pipeline. And then you can easily scale out this pipeline by specifying the number of replicas. And then you can change the batch size to trade off between the fault tolerance and the throughput. And the rest of the thing will be handled by RayLLM batch. Specifically, we will optimize the engine configuration, and then we'll deal with the scalability and the fault tolerance. And again, RayLLM batch is already available on the Anyscale template, so feel free to take a try and do talk to us if you have any feedback or you need any supports. And here are some early results from the RayLLM batch. You probably already seen these figures shown by Richard in the keynote this morning. Specifically, when benchmarking Llama 3.1 on L40 GPUs with the 2,000 input and 100 output, we can see that with the RayLLM batch, we can have 3x cost saving compared to Bedrock batch API costing. And then, like Richard showed this morning, usually your prompt has a lot of prefix sharing. So suppose your prompt has a very long instruction that's being shared across all the requests you have, and this is 80% of your total prompt length, then you can actually get another 2x cost saving. So you'll be 6x compared to the Bedrock batching API. So there are a lot of potential of the cost saving used in the batch inference, and it's really workload dependent. And the RayLLM batch is offering a customizable solution for your particular use cases. And the next feature I want to introduce is Anyscale JSON mode. So let me first introduce the JSON mode. JSON mode actually enables LLM to produce the JSON format responses. And this is the critical feature to integrate LLM with other systems that consume the LLM output. In other words, this is actually very critical if you want to build the AI agent with LLM. For example, you may want to ask LLM to output or analyze a certain article or customer data, and you want the LLM to output a certain JSON format with the analysis results, and you want that result to be passed by another system component for further data processing or whatever the action you want to take. So you have to let LLM to strictly follow the JSON grammar so that your rest of the system components can consume that without any problem. Then how to achieve the JSON mode? Intuitively, most solutions out there is actually embracing the finite state machine-based solution. Specifically, you'll provide the JSON schema, and the JSON schema will be converted to the regular expression. And based on the regular expression, we will construct a finite state machine. Each state in this finite state machine basically says what's the tokens is available for your next generation. So once you construct this finite state machine, during the decoding phase, you're just traversing this finite state machine and tell the model, at this moment, you can only choose from these 3 candidate tokens, but not any others. This solution works well, but you can imagine the major problem of the solution is you have the cold start, especially if your regular expression is extremely complex. So in Anyscale, we took another algorithm, which is called token tree traversal, in short T3. Instead of constructing an entire finite state machine in advance, we actually construct and figure out the finite state machine on the fly. So we will determine the next state based on your current status. In this way, we can support a much more complex grammar in GBNF. For example, you can even put the entire Python language grammar in this JSON mode. It's not JSON mode anymore. It's basically a Python mode. So yeah, and then you can imagine in this way, you have to construct this state on the fly. So this will bring additional overheads. And then we solve this by introducing the asynchronous token tree traversal. So we're generating this state along with the model forward. So we'll keep both CPU and GPU busy and purely hide this generation latency. And then, of course, we can distribute this token tree processor easily with Ray. And this feature is also available on Anyscale, and we'll publish more details in our blog post very soon, so stay tuned. Last but not least, the last feature I want to introduce today is the fast model loading. Again, why fast model loading? So you imagine you're serving a private endpoint with certain replicas, and it has to make sure all the requests are within the certain SLA, let's say 1 second. You may calculate the number of replicas you need over the time, but you may have some spike traffics depending on special events. So in this case, you will need auto-scaling. However, if you just simply use the auto-scaling, that will try to open more replicas when there are more traffic coming in. You may take 5 to 10 minutes to get the new replicas up and running. Because every replica will need to download the model weights from your cloud storage, for example, Hugging Face Hub or whatever storage you're having, and load them to the GPU memory. And if you need to take 5 to 10 minutes to make those replicas available, you may not be able to efficiently respond to the request traffic changes. And in Anyscale fast model loading, we actually embrace the optimal model layout and the network utilization so that you can load the model and let the replica up and running with 4x and 5x speed up with the 7B model and the 70B model respectively. So by this result, we can see every replica can be available within 2 minutes. So it's actually pretty efficient and made the auto-scaling more practical in your business use cases. And then we do have the demo on the RayGround and Ed will be there, so feel free to talk to him if you want to try out this feature. Okay, so lastly, I want to introduce 2 preview features which are not available in the Anyscale platform yet, but it will be available soon. If you're interested in those features, feel free to talk to us and we'll introduce more. So the first one is the custom draft model for speculative decoding. Philipp just introduced speculative decoding. It sounds very attractive. You can get 2x or even more ITL reduction by introducing a small draft model. But in order to achieve that speed up, you better have a customized draft model for your particular downstream tasks. So that means you have to train that small model by yourself. But in Anyscale, we offer an end-to-end solution in the Ray Turbo. Specifically, you will first have your target model ready, and then you can use the RayLLM batch to collect the output and the responses of this large target model. And then you can use LLM Forge, which is a Anyscale fine-tuning solution to train a small draft model with the cost-effective. And again, LLM Forge is available in the Anyscale booth in the RayGround, so feel free to check out, and we have the live demo there. So it will show all the details of the LLM Forge. And after you get the fine-tuned draft model, your customized draft model can be deployed along with the target model using RayLLM. So this will become a fantastic end-to-end solution provided by Anyscale. So do talk to us if you're interested in this. In addition to that, as I just mentioned, in the batch inference case, because we can optimize the engine configuration based on your use cases, the throughput can be significantly different with and without the optimization. It can be as different as 2x or even more. So in order to figure out the best configuration, particularly for your workload, we are offering the engine configuration optimizer, which will basically explore and optimize the engine configurations to minimize the cost only for your workloads. Specifically, you need to provide the model you want to use and a small set of the sample data. And then the inference engine optimizer will actually choose the best GPU type, the best preference strategy, and so on, and then figure out the best configuration. And then you can just simply feed this configuration file along with the workload you just defined to the RayLLM batch, and everything will just work. So again, this is a preview feature. So if you're interested in that, do talk to us for more information. Okay. Finally is a takeaway. Then I'll hand back to Philipp.
So we showed you that we are very invested in the open source community to make vLLM, to contribute to cutting edge LLM optimizations to open source. That includes things like FP8 support, chunk prefill, multi-LoRa support, speculative decoding, multi-step scheduling, and many others. And at Anyscale, we also innovated all levels of the stack to make Anyscale the best place to run for LLM inference. This includes inference-level optimizations to co-optimize what kind of GPUs are run with engine configurations, to do fault tolerance, autoscaling, to have very good monitoring observability. And then also, we've been working on a lot of inference optimizations that make the inference even faster, including optimized kernels, the JSON mode, and then optimizations for batch inference and online inference. Thank you so much.
Thank you.
All right, for Q&A, please use this microphone so we can record your questions.
Yeah, thank you for the great presentation here. I had a question about these inference engines, because which are cropping up all over the place. Pinecone, for example, has got an embedded inference engine. Anyscale is kind of like coming up. So for the people who are adopting this, what is your take on this? Like, which way do we sway? Towards the database side, or is it more on the compute side?
I'm not sure if I understand the database analogy. Are you asking like what kind of inference engine will be the best, or whether it will be proprietary or open source? I mean, the way that we view the inference engine in terms of proprietary and open source, we do think that there's a lot of value from the open source community, and covering all the different use cases with some generic inference engine like vLLM is like extremely good. But we are also working on proprietary optimizations for the best, as I showed, for getting the best performance for specific models and specific features. So, yeah.
For the token tree traversal T3, for the T3 traversal, does it work with speculative decoding? Can you generate the tree k steps ahead?
Yeah, this is a good question. So the question is whether the JSON mode with the T3 algorithm is compatible with speculative decoding. The short answer is no at this moment, but there's nothing fundamentally prevents from doing that. Specifically, what you need to do is you need to traverse the algorithm, traverse the tree, and then along with the speculative tokens, but you need to provide the capability of falling back if that token was being rejected. So this is definitely on our roadmap. So stay tuned. If we have anything new to release, yeah, we'll let you know.
So I have a question about that engine optimization that you had in the previous slide. Like, what are the hard SLAs that we can set in order to do this optimization? What is the metric for optimization? Is it dollar spent? Is it time? Or can we set that? Is that configurable?
Yeah, this is also a great question. So in short, the question is about what's the metrics used in the engine optimization. So first of all, the objective function should be able to set by users, but the most reliable metrics we're having right now is the cost per million token processing. So this will consider the different GPU instances price and the model you use and the prompt you use. So it's highly effective by, for example, the length of your input tokens and the length of output tokens, and how many shared tokens in your input prompt, and et cetera, et cetera.
What about like performance on benchmarks, like more aggressive quantization?
Yeah. Yeah, it's also a good question. So the question is whether the engine optimization will consider the model quality if we enable the quantization. Yeah, so this will be definitely another metrics if we choose to enable certain quantizations. So we will consider for example, you can provide the set of benchmark sets, and then we will first evaluate whether the certain quantization is acceptable. If so, then we will add it to the exploration space.
And for most of the optimizations that we work on, we try to really get it all, and like spend most of the time on quantization schemes that are as lossless as possible, like FP8. And then for the inference optimizations, like use as few instructions as possible. That makes it both fast and cost effective. But sometimes there are trade-offs, like speculative decoding, for example. If you activate that, you're going to pay more because you will have some retracted tokens, and like you will need to run the draft model. So like that's where the flexibility comes in, right? And like if the user decides that they want to take these trade-offs, then they can. But by default, we try to optimize as much as possible without too much trade-offs.
Yeah, my question is about the FP8 support. So you included FP8 support as part of your open source feature, but it's also listed as a proprietary feature. And this morning, the speaker keynote mentioned that FP8 is actually part of TurboRay that is arguably by default enabled on Anyscale. So my question is, what is the difference between the FPA that we have for quantization in the open source versus the one we have on Anyscale? And based on your answer, probably I'll have a follow-up there.
Yeah. You want to take it?
So the Anyscale version goes a little bit farther in certain cases where we can fuse together more stuff due to how we write the code. Like with the open source stuff, we go as far as the open source kernels allow us. But like there are some optimizations we can do that are just possible because, and actually this is a larger project that throughput has been leading. He sits in the back, so if you have more questions about that, he will be a great person to talk to about that. It's actually very impressive. Like it's basically rethinking how the inference is being done and like writing everything from scratch. And there's a decent amount of optimization that we can do there that are not possible in the open source codes.
All right, another round of applause for Philipp and Cody. Thank you.